Hello everyone, this is Dhanlakshmi, Assistant Professor of Cookery Department from Madam Engineering College. In this session, I would like to discuss about AC voltage controller. So, in the subject power electronics and Unit 5, where in Unit 5, as in the other video, I've told you already discussed that Unit 5 can be divided into two major sections, where one is the AC voltage controller, the other one is the cycloconverter. In that video, we have discussed about cycloconverter, and in this today's video, we will discuss about AC voltage controller. So as the name itself tells us that AC voltage controller is it's a one where it is going to convert the fixed AC to variable AC without change in frequency. So it's a AC voltage controller where it is where the input is also AC, output is also AC. So where the input is a fixed AC, that will be converted into variable AC at the output without change in frequency. Here the frequency is not going to change. The frequency will be a constant one. So without changing frequency, then we are going to convert the fixed AC to variable AC with the help of the AC voltage controller. Right? And we'll see how it is working. And these are the applications of AC voltage controller, where industrial heating, transformer tap changing, lighting control, speed control of single phase and three phase drives. So starting of induction motors, all these are the applications of AC voltage controller. Right. So when we take AC voltage controller, here we can have two types. One is the single phase half wave AC voltage controller. The other one will be the single phase full wave AC voltage controller. First, let us discuss about the single phase half wave AC voltage controller. It's a very simple circuit, and one best example for okay, as when we go for a full wave, that time we can discuss it. So here we can see that here we have the supply. One second. Yes, let me take a time. So here we have the supply. The supply is a fixed AC, and this is our AC load, right? A resistive AC load. So here we can see that since it is a single phase half wave, so which means that actually the AC voltage controller general configuration of this is where we are going to connect two switches anti-parallelly. That is two SCR connected anti-parallelly. Right, so it is back to back. But here, for since it is a half wave AC voltage controller, so one will be a thyristor, the other one will be a diode, right? So if you are going to connect a thyristor and diode back to back, that is in anti-parallel form, and this is the configuration of a single phase half wave AC voltage controller. So on this side we have fixed AC input, and here where we have to convert this fixed AC to variable AC with the help of this single phase half wave AC voltage controller. In this half wave AC voltage controller, where we have a thyristor and a diode connected back to back in anti-parallel fashion, right? So here the logic is so here let me take this. Yeah. So here we can see take that here we can. Here we can see that the AC voltage is given. One second, let me take the right. So here let me take that initially the positive half cycle is coming out, right? So let me take let us discuss for one full cycle. So initially let me take that I have a positive half cycle. So when I'm getting positive half cycle coming out from the supply, so here the polarity will be positive and here the polarity will be negative. So as we know that the positive polarity connected to thyristor T1 as well as to the diode D1. So as we know that when the positive half cycle is coming out from the supply, thyristor T1 is forward bias, whereas the diode D1 is reverse bias. Right? So therefore the thyristor T1 is now ready for the conduction, and as you trigger it, as you apply the gate pulse here, the thyristor will be conducting. So as you see that, so at the instant alpha, you're going to trigger it. That alpha is the beginning angle or the firing angle, or the instant at which you're going to trigger, it starts conducting. So therefore from the instant alpha, here you can see that I'm getting my output voltage, right? So because in positive cycle, that is during positive half cycle, the polarity here will be positive and here it will be negative. Thyristor T1 is ready for conduction because it is forward bias, and diode D1 is reverse bias. So therefore, as you apply the alpha, that is triggering angle or firing angle at the instant, at the instant wherever at the desired instant, it starts conducting. So therefore, at the instant alpha onwards, I'm getting my output voltage. That is the input is merely transferred to the load. Right? Whereas during the negative half cycle, as we know that immediate to the positive half cycle, we'll be having a negative half cycle. As the negative half cycle is going to come, what will happen now? The polarity here is you can see that now here the polarity will be negative. and here the polarity will be positive. As the negative polarity comes here, which means that the negative half cycle, whenever the negative half cycle is coming out from the supply, now thyristor T1 is reverse biased and diode D1 will be forward biased. So here you can see that before in the positive half cycle, the current is flowing from supply to the thyristor T1 and to the load R like this in this direction. So that's why we got our voltage in this direction as well as the current in this direction, because my load is R load, so both voltage and current are in phase with each other. Whereas during the negative half cycle, as we can see here, the polarity has been changed. So here it is negative, and now here this terminal will be positive, which makes thyristor T1 to be reverse bias and D1 to be forward bias. So now the conduction will be from the supply through the load and through the diode D1 and to the supply back again. So now you can see that the direction is reversed here. Now the direction is reversed here, which means that is from the supply to the load to the diode and back to the supply. So therefore, I'm getting the negative half cycle like this. Since it is a diode, this will conduct from the instant pi itself. So here we don't have the alpha. Right. So for the negative half cycle, we don't have the control. We have control only during the positive half cycle. Right. So that's why it is said to be half wave AC voltage controller. Only half the wave can be controlled, whereas the negative half cycle is negative half cycle. During negative half cycle, we cannot control it. Right. So only during positive half cycle there is a control available, because the device which is going to conduct will be thyristor T1. Whereas during negative half cycle, the device which is going to conduct is our diode D1, where we don't have any control over it. So therefore, we will be getting the negative half cycle from the instant pi itself. From pi to 2 pi, we have the negative half cycle passing to the transfer to the load. Right. So this is the idea. So where we can again during positive half cycle, thyristor T1 will be conducting, and during negative half cycle, diode D1 will be conducting. So that's why the name is given half wave, because only positive half cycle alone will be controlled. But the negative half cycle, we don't have any control over it. Right. So having this in the mind, and just by seeing the waveform, now we want to derive the average value and the RMS value. Right. So now we want to derive the average value and the RMS value. As we know that for deriving average value and RMS value, the formula, as we know, the square root of area of the squared curve divided by base. So, right, that is the formula, we know it already. So one second, let me. Right, so we can see that here up to alpha to 2 pi. Yes, we have to take the waveform from alpha to 2 pi, because the waveform is getting symmetrical only after 2 pi, not before that. So we should be very careful in that, right? So for finding V naught RMS, the formula is square root of area of the square divided by base. So here I have to take the base as 2 pi, right? Here I have to take the base as 2 pi, and I'm getting my waveform from alpha to 2 pi. So my limits should be from alpha to 2 pi. So these things we should keep it in mind. Yes. So therefore, we should take our base as 2 pi, and we should take our waveform, that is limits should be from alpha to 2 pi. Right. So now we will go for the derivation of average and RMS value. So here we can see that as we know, the formula is square root of 1 by 2, right? Square root of area of the squared curve divided by base. So here the base is 2 pi, as I told you already. The base should be 2 pi, and the limits whatever we have to take here is alpha to 2 pi. So that's why. So here you can see that the base is 2 pi, and here we are taking the limits as alpha to 2 pi, because we are getting our waveform from alpha, and we are getting the waveform continuously up to 2 pi. So that's why the limit should be from alpha to 2 pi. So just see the waveform. Here you can see that waveform we are getting from alpha, and it is continuous up to 2 pi. So that's why we are taking the limits to alpha to 2 pi. And according to the formula, it is square root of area of the squared curve. So we are squaring the curve. Our curve is Vm sin omega t, because it's a AC wave which is transferred. So our curve is Vm sin omega t. So we are squaring it, Vm square sin square omega t. In order to find the area, we are integrating between the limits alpha to 2. Right? As we simplify this, we will get our V naught RMS to be this one. Right? So what we have to do, we have to take Vm square outside. Then sin square omega t can be written as 1 minus cos omega t by 2. So right, before integrating, we are going to convert the sin square omega t term. So that is 1 minus cos omega t by 2, and this 2 we already have taken out, so it becomes 4 pi l. Now we have to integrate, and after substituting the limits, we will be getting our V naught RMS in this form. Right? So this is the expression we are getting for V naught RMS, what is RMS value of Right, so this is the RMS value we are getting for our half wave. Right. Now, the same way for the average value. So here we can see that for average again, the formula is the same. Again, for RMS, the formula is square root of area of the square curve divided by base. But for average, the formula is area of the square divided by base. Again, here the base will be 2 pi and we want to find out the area of the curve. So the curve is Vm sin omega t, and to find the area, we're going to integrate it. Where we are getting the curve from alpha, and the curve ends up to 2 pi, right? We're getting the curve up to 2 pi. The curve starts from alpha and it goes up to 2 pi continuously, right? So that's why we're taking the limits to be alpha to 2 pi. Again, taking this Vm outside, and if you integrate the sin omega t and if you substitute the limits, we're getting our V naught average. That is our output average value to be Vm by 2 pi into cos alpha minus 1. So here we can see that. Now we'll go for the next configuration, which is our single phase full wave AC voltage controller. As we discussed already, the half wave AC voltage controller, there's only one difference we can find between the full wave and the half wave. Where in the half wave, only half of the wave can be controlled, but here both full wave can be controlled with the help of having another thyristor in the reverse bias direction, right? Sorry, another thyristor in the reverse cycle. That is, there we have one thyristor and one diode connected anti-parallelly. But for full wave AC voltage controller, what we're going to do is we're going to have two thyristors connected back to back, right? So the difference what we have between half wave and full wave is in half wave, it is a thyristor and diode combination connected anti-parallelly. But in case of a full wave AC voltage controller, here we're going to have two thyristors connected back to back or two thyristors connected anti-parallelly. Right. So the idea here is we're going to control both the half cycle. Where in half wave AC voltage controller, we can control only the positive half cycle. Where negative half cycle, we don't have. So in full wave, single phase full wave AC voltage controller, where we can see that both are thyristors. Thyristors will be conducting in both the half cycles. Here once again, let me take the answer. Yes. So here we can see that for half wave cycle, in single phase half wave AC voltage regulator, where we have one thyristor and a diode connected anti-parallelly, whereas here two thyristors connected anti-parallelly, that is back to back. So here the positive cycle will be conducted by thyristor T1 in this way, whereas the negative cycle will be conducted by thyristor T2 in the opposite direction. So here the logic is where both the cycles will be controlled. So positive cycle by thyristor T1 and negative cycle by thyristor T2. Whereas in case of half cycle, only positive cycle alone is positive half cycle is alone is controlled, whereas the negative half cycle where it is conducted through the diode, so there is no control over the negative half cycle. But whereas in case of full wave AC voltage controller, both the half cycles are being controlled by thyristors T1 and T2. So thus we get the controlled waveform in the negative cycle also, as like in our positive half cycle. So therefore here we have to take the limits to be from alpha to pi, right? So that is alpha to pi. We should take it for a half a cycle because the waveform gets symmetrical in the half cycle. So therefore we can take the limits from alpha to pi. Whereas in half cycle, where we took the limits from alpha to 2 pi, now we are going to take the limits from alpha to pi, because here we can see both positive half cycle as well as negative half cycle, both are get controlled. So therefore, when we so when we take the RMS, or when we want to find out the RMS value here we can see that the limits are taken from alpha to pi and the base is taken for pi, because half a cycle, the symmetricity exists for half a cycle. So that's why we take the base as pi and the limits from alpha to pi. Then as we know that the formula for RMS value, square root of area of the squared curve divided by base. So here the base is pi, the square root of area of the squared curve. The curve is Vm sin omega t. So when we square the curve, it is Vm square sin square omega t. Here we are taking the limits of curve to be from alpha to pi. So because the wave gets symmetry in the half a cycle. So when we solve it, we got this expression for V naught RMS, and since the wave gets symmetry at 3 pi itself, the average value of the output voltage will be 0. Thank you.